So this lecture is 7.3 from your textbook. It's on electric fields. So almost everywhere you go, you'll find a device that makes use of an electric field of some kind. The electric field is what causes the electric force. You can kind of think of the electric field as it's an area where there is a potential for an electric force to exist. If you consider a gravitational field, it's the area around an object like the Earth where there would be a gravitational force. And the electric field, each object kind of that's charged generates its own electric field. So it becomes an electric source, kind of like how the Earth is a gravitational source. Now the range of the electric field, the range of the gravitational field is infinite. But the farther you get away, the less effect that electric field has. Now going back to devices that you would know that use electric fields, there's some examples given on this slide. An X-ray machine. What it's doing is it generates an electric field that accelerates electrons really fast to produce X-rays. A coal-burning power plant will have a lot of exhaust, and that black exhaust that you see contains a lot of particles that are charged particles, and to remove those charged particles we use things that are called electrostatic precipitators. And those electrostatic precipitators generally, it's an electric field that's generated inside of the smokestack that sort of filters out the electrically charged particles that are bad for the environment. A telephone, this is an old rotary telephone that's shown here. Basically what happens with a telephone is it converts your sound into an electrical signal and then back to sound again. And this is done through the use of an electric field as well. So I'd like you to copy this down. Electric field, the symbol you see there is epsilon. It's a field of force that exists in a region of space around a charged object. The electric field is a vector quantity, and it exerts either attractive or repulsive forces on other charged objects. And this is, again, it's attractive if the objects have opposite forces. If the objects have opposite charges, and it's repulsive if they have alike charges. Next thing it says here, it says LCDs use changing electric fields to alter the crystal's optical properties, creating images. That's not necessarily something you need to copy down, but that's just another kind of note. So this diagram here kind of visually sort of explains what an electric field looks like. And we have a charge, that Q1 in the center. The dots around it sort of decrease in density the farther you are from the source. So that's showing that the electric field is stronger closer to the source and weaker farther away. And if we have another charge, so that's Q1 is the source. If we have another charge Q within that electric field, it will experience an electric force, an Fe, and if Q was negative, then it would be, if it was positive, then it would be repelling the away from Q1, and if Q was negative, it would be going towards. So that Q, we call that a positive test charge, and it's in general we treat it as positive. So anytime we are in an electric field that is a positive electric field, it would be repelling away from the source, and anytime we're in a field that's a negative electric field, that positive test charge would be attracted. So this is that's the convention we use. I think it gets explained here, and it does actually. So it says, to describe the field around a charge Q, it is convenient to use the concept of a positive test charge. By definition, a test charge, QT, is a point of charge with a magnitude so much smaller than the source charge that any field generated by the test charge itself is negligible in relation to the field generated by the source charge. So this positive test charge, consider its electric field to be so weak that it doesn't have any effect on the positive, on the larger charge that we're looking at, that Q, that plus Q. So the electrostatic force Q times epsilon, if we relate that to the other way of calculating it, which is K times Q over R squared, we can end up getting a different formula, epsilon equals K Q over R squared, to find out a way to calculate our electric field from a positive test charge, or from not a positive test charge, but for any charge, the electric field generated by it can be calculated as K times Q, which is the magnitude of the charge, divided by the distance to a positive test charge. So a positive Q, the electric field, because we always use a positive test charge, we show the vectors coming from a positive charge as being repulsive vectors, and for a negative Q, we show the field lines as being attractive, so they're pointing into. So this is the equation for electric field intensity. Epsilon equals KQ over R squared. Epsilon also equals FE over Q. Epsilon is the electric field intensity. It's measured in newtons per coulomb. K is Coulomb's constant. Q is the point charge, and R is the distance between the point charge and the source. Another thing to note is if we rearrange this equation, we get FE equals Q epsilon. So that is similar to F equals MA. And basically, this is kind of how I consider it to help me understand, and I think it helps students as well. But your M, your mass, is related to your Q. When we're talking about the electric world, Q is our M. So the amount of charge we have is similar to the amount of mass we have. And the epsilon is similar to your A. So your newtons per coulomb is similar to your meters per second squared. It's similar to your acceleration. So to find an electrostatic force in an electric field, we simply multiply the amount of charge of the point charge by the epsilon, which is similar to our acceleration at that location. That might help you understand this a bit more. So you can kind of think of your epsilon as your acceleration, and you'll notice that your electric field intensity is very similar to your gravitational field intensity. So whereas gravitational field intensity, which is newtons per kilogram, electric field intensity is newtons per coulomb. It's basically force over charge or force over mass. And it's also calculated as your constant times your charge over R squared, so KQ over R squared, or your constant times your mass over R squared, so KM over R squared. So there's a very close relationship between electric field intensity and gravitational field intensity. And that implies a close relationship, or a similar relationship between epsilon and acceleration. So here's a question. It says there's a positive test charge. It is a QT. Magnitude is 2 times 10 to the negative 9. And it's placed in an electric field, and it experiences this force of 4 times 10 to the negative 9 newtons to the west. So what is the electric field intensity at that point? So it's basically our force, 4 times 10 to the negative 9, divided by 2 times 10 to the negative 9. And the 10 to the negative 9s will cancel out. So it's 4 divided by 2. So we have 2 newtons of force per coulomb, and because the force was in the west direction, the epsilon is in the west direction. So think of it as, if you thought of it as an acceleration, if we're experiencing a force of 4 newtons to the west, and our mass was 2 kilograms, then we must have an acceleration of 2 newtons per kilogram, or 2 meters per second squared would be our acceleration. Yeah, the next part of this question says, what would be the force if we had a test charge of 9 times 10 to the negative 6? So we now know that it's 2 newtons per coulomb. So we take that 2, we multiply it by 9 times 10 to the negative 6. We get 18 micronewtons, or 1.8 times 10 to the negative 5 newtons, and that would be in the west direction. Another thing to note here is that electric fields, if we have a singular charge, it's simple. It's either it's kind of the forces, the vectors are circular. They're all either pointing in or pointing out. If we have 2 charges near each other, we have more complicated fields. So the field for a positive charge is lines radiating out. So if we have 2 of those next to each other, we would have this kind of arrangement. But now what we're interested in is, what is the charge, what is the force experienced by a point charge at a specific location? And it will be directly away from Q1. It will have a force that will be opposed. And it'll have another opposing force for Q2. But we'd have to add these together to find out what our net force is. So here we have 2 point charges, and they are located 45 centimeters apart. And we have a positive test charge that's located between Q1 and Q2, and it's 27 centimeters along Q1. So what we're going to do, let me draw this, and we'll understand this a bit better. So we have a Q1 and a Q2, and then there's a charge located between them. So here's our Q1. Here's our Q2. Q1 and Q2, they are 45 centimeters apart. Somewhere between them, it says a positive test charge located between Q1 and Q2, and it's 27 centimeters from Q1. So this we're going to call Q, and the distance to here is 27 centimeters. What is the net electric field intensity on this positive test charge at this location? So the force from 1 is going to be we have Q. So what is the epsilon, not the force? The epsilon experienced here is K Q1 over R squared. And then the epsilon at 2 is K Q2 over R squared. So K, I'm just going to write down K. It's 8.99 times 10 to the negative 9. Q1 is 3.3 times 10 to the negative 9. And the distance between these two is 27 centimeters. Here we have K. Q2 is 1.0 times 10 to the negative 18. 10 to the negative 8. And Q is 45 minus 27. I'm just going to do this really quick. 45 minus 27. It's 18. 0.18 squared. So we'll evaluate these, and then we'll figure out which direction they go. So 3.3 times 10 to the power of negative 9 times 10 to the power of 9 times 8.99 divided by 0.27 squared. So here we have a charge of 406.95 newtons per coulomb. Over here we're going to have 8.99 times 10 to the power of 9 times 10 to the power of 8 negative times 1 as well, divided by 0.18 squared. And over on this side we have 2774.7 newtons per coulomb. This direction, right, so Q here, Q2 is negative. So this Q is going to be pushed towards that. It's going to be attracted because it's a positive charge. Q1 is positive. So this Q is going to be pushed that way. So these are both operating in the right direction. So my total epsilon net is the vector addition between epsilon 1 and epsilon 2. So it's going to be 406.95 plus 2774.7. So this value plus 406.95, and then I round for two significant digits, so this becomes 3.2 times 10 to the negative 3, or sorry, 10 to the power of 3 newtons per coulomb to the right. Okay, now this question, we have a diagram. A and C are situated as shown, and it says, what is the magnitude and direction of the electric field intensity at point B? So B is is our positive test charge. Let us, well, I guess this doesn't really help, so we'll just expand this. Like that, so we can see a bit better. That was our previous question. Okay, so now let's solve this problem. We have our A and C are located at different locations here. B is 3 centimeters away from C. So we have F of C on B, and that is going to be K. Oh, actually, sorry, we're finding the electric field intensity. So that's epsilon of C on B is KQC over RC squared. And then epsilon of A on B is KQA over RA squared. So let's figure what both of these are. This is K. QC is 82 microcoulombs, and the distance between is 3 centimeters. And over here we have K, we have 46 rather, not 64, 10 to the negative 6 coulombs over the distance between, which is 4 centimeters. This then gets us to let's see here. We've got 8.99 times 10 to the power of 9 times 82 times 10 to the power of negative 6 divided by 0.03 squared. So this is a rather large value. So I'm just going to write it down as I'll write down 8.191 newtons per coulomb, and we'll work on the direction after. And then the other side we have 8.99 times 10 to the power of 9. So 8.99 times 10 to the power of 9 times 46 times 10 to the power of -6 divided by 0.04 squared. So this is 258 50000 newtons per coulomb. And the direction here, so C was above B. I'll bring up the picture again just to show you. C was above B, so and C was, in this question, C is positive, B is positive, so that means that this is going to be operating, or going to be going down. B was positive 46, so that means that this is going to be repelling as well. So now I need to, sorry, let me go back here. That was, I forgot to write the order for this. This was times 10 to the negative, times 10 to the power of 8. So I now have to find out what epsilon net is, and it's the square root, it's the vector addition between these two, which works out to the square root of their magnitudes, the square root of the sum of the squares of their magnitudes. And this works out to the square root of 8.191 times 10 to the 8 squared plus 258500000. I don't know why I didn't write that in scientific notation, but so this is this value squared plus 258500000 squared. Then I find the square root of that. I end up with 8.6 times 10 to the 8 newtons per coulomb. I then also have to find out what my direction is, so I will do a quick little side calculation. It's the inverse tangent of the smaller, which is 8.191 times 10 to the 8 over the larger 258500000. So I would take this value and divide it by 258512123, and then I would inverse tan that. Actually, I did it the opposite way around. And I get 72. Let me just subtract 90 from that. I get 17, which works out to about 18 degrees. And this is then 18 degrees. It's going to be going more towards the, so here's where I put my solution. So it's going to go more towards the right, and then it's going to make an 18-degree turn down. Because this was the larger value, so it goes right first, 18 degrees, the other value down. And that's our solution here. So some applications of electric field. You may or may not know that the Earth's atmosphere, we have harmful particles that are, or harmful charged particles that are reflected or deflected from the Earth's ionosphere. Basically, that kind of protects us from a lot of cosmic radiation. So that's one kind of application of the Earth's electric field. In an engineering application, we have the electric field mill. So electric field mill is a device that measures the Earth's electric field. Basically, we don't have to know exactly how it works, but it detects the electric field change between two parallel conducting plates, and then it will determine the field strength at a given location based on that. I mentioned electrostatic precipitators earlier. Basically what they do, we put these in flues of chimneys, and they will, the gases we do not want brought out into the atmosphere are nitrogen and carbon dioxide, but there are also tiny carbon particles and sulfur particles. And these are often electrically charged. So with an electrostatic precipitator, which is essentially an electric field, it will attract those particles, and they will not go out inside the smoke. This goes a bit further into how electrostatic precipitators work. You really just need to know what they are in terms of this course. If you're really interested, you can, I think, you can do some research yourself, but I just need you to know what they are. There are animals that apply electric fields as well. The hammerhead shark actually detects a very low electric field of 6 newtons per coulomb, and it can actually find fish in the sand by kind of determining with a special organ how much resistance they get from fish that are generating an electric field as well. So this slide, I'd like you to copy down some applications of electric fields. We have X-ray machines, LCD displays, telephones, particle accelerators, electrostatic precipitators. There are organisms that use electric fields to detect other organisms. There's also, we didn't talk about it, but there's musical instruments such as the theremin that uses an electric field as well.